Hello everyone. So in the last session we have gone through that intersection of context-free language with a regular language is a context-free language. And we have taken the example of a PDA and it is having an intersection with a regular language, that is finite automata, and we found that we are getting an intersection as a context-free language. The PDA which was taken was a odd length palindrome. Then another one FA was that was ending with A. When we are getting the intersection, we are getting any string which begins with A and ends with A, right? So that is what we have got as an intersection of CFL with a regular language, and which is a CFL. So today we'll see some more interesting things about the context-free language. But before that, we have to cover this small topic. That is, in the top-down parsing, we have discussed about the left factoring of the grammar, right? That how to left factor the grammar in the previous session, when we want to eliminate the non-determinism, and we have seen that the left factoring plays an important role. That up to some level, we can remove the non-determinism from the grammar by left factoring it. And another important term was elimination of left recursion. So today we'll see what is the left recursion, how to eliminate the left recursion from the grammar, and also we'll discuss about a pumping lemma for context-free languages. So now let us understand what is a left recursion. So basically a production of the form A gives A alpha or beta. When we see a production like this, A gives A alpha or beta, then we can say it is a left recursive production, because the leftmost non-terminal is the first symbol in the right hand side, right? The non-terminal of the grammar is appearing as a first symbol in the right hand side in one of the productions. You can see capital A produces capital A alpha. Capital A produces capital A alpha or beta. So you can see that the capital A, which is a non-terminal, which is repeated, and we are getting the same non-terminal again over here, right? So this A is repeated here. So that's why it is known as a left recursive. Now, what is the problem with this left recursive grammar? That when we want to do a derivation, right, then this kind of production will lead us to infinite loop. So we can see this one such example of a grammar where E is replaced with E plus T or T, right? So you can match A with capital E, alpha with plus T, and beta with T, which is a non-terminal. So suppose if I want to use this kind of production in any leftmost derivation, then what is the rule? That we have to always give a priority to the leftmost non-terminal. So here, from the leftmost non-terminal E, we are again getting the same leftmost non-terminal E. E gives E plus T. So same thing is repeated. Again, we are getting the non-terminal E one more time. And because of that, we are getting the patterns like again E plus T. So we are never getting a terminal symbol. So when one of the productions in a grammar is left recursive, then a top-down parser during leftmost derivation loops forever. As you can see here, from E, we are replacing it with E plus T, which is a leftmost derivation. Then again, we have a leftmost non-terminal as E. So again, I have to replace it with the production rule. So I will replace with E plus T. Again, I am replacing E with E plus T because it is a leftmost derivation. So we will go into infinite loop, and this will never end. And if we replace forcefully to stop this infinite loop E with T, then we are getting T gives plus T plus T plus T like a pattern. So basically what it tells that when we have a left recursive grammar, we have a certain pattern which is repeated. we have a certain pattern which is repeated. It is plus t any number of times. It is plus t which is repeated any number of times. So basically the main thing is when we have a left recursive grammar, so when we do this, right, but computer cannot decide when to stop. As a human, you know that now I can stop, I can replace e with t. But as a computer algorithm, when you implement, right, because they don't know what is the actual statement which you want to derive, we are always looking at one symbol at a time, right? In the push down automata, we have seen that we are always looking at one symbol at a time from the input pattern. The input pattern may be very large. So computer cannot take a decision when to replace e with t to stop the recursion. So it will go into infinite loop. So we have to remove this kind of situation from the grammar rule. So don't confuse this with the left factoring. In left factoring, what we have discussed, that two alternatives are same, right? Two alternatives have the same form. Both begins with the same symbol. So we have a confusion. Which alternative is correct? Here in left recursion, you can see the alternatives are different. E plus t or t. Here our alternatives are different, right? E plus t or t. But the problem is that when we are dealing with this, right? The problem is here we have e plus t and t, but we have a leftmost non-terminal, which is same as the non-terminal. So we are getting an infinite loop. While in case of left factoring, two alternatives begins with the same symbol. It creates a confusion that which alternative is applicable at a particular given point. So that is the difference between a left factoring and left recursion. So now we have a rule to eliminate the left recursion from the grammar. So let us see that how we can do that. So this kind of grammar rule, having an immediate left recursion problem, we have this rule that we have to rewrite every left recursive production. You can see the left recursion here. A gives A alpha or A delta. These are the two productions which are left recursive, while beta and gamma, this beta and gamma are not left recursive productions. So we have to write into another form which is known as a right recursive production, right? We'll rewrite into a right recursive form, because in that case the recursive symbol will be at last, so it will not create any problem. It will not create any problem. It is the last option we have to apply. So what is the rule? We'll write as A gives beta AR. So beta is the rule in which there is no left recursion. We have beta AR. We'll introduce a new non-terminal. Another is gamma. So it is gamma AR. We are introducing a new non-terminal AR. And for AR, and for this AR, we'll write the remaining portion from the left recursive rule. So we'll write alpha AR. We are writing as alpha AR and delta AR. Delta is the remaining portion from the left recursive rules. And we have null to terminate this process. To terminate this process, we have to write null here. Otherwise, it will go again into infinite loop. There is no termination for non-terminal AR. So here you can see that if we have this rule, E gives E plus T, E minus T or T. So here you can see that it is a left recursive grammar. It is a left recursive grammar. E gives E plus T, E minus T or T. So now what we have to do, that from this if we match, then A matches with E, alpha matches with plus T, delta matches with minus T, and beta matches with T. If you compare with this, so beta means the production rule in which there is no left recursive part. So we'll write that E gives TER. We'll write as E gives TER because T is your production rule in which there is no left recursion. In which there is no left recursion. So we'll write as TER. And now for this ER, we'll write the remaining portion, A alpha. So remaining portion is plus T. So we'll write plus TER. Then from The second rule, A delta, we'll write delta. So delta is minus TER, and then we'll write null to terminate the recursion. So this is how you can see that we can eliminate the left recursion. This will not change the meaning of the grammar. The grammar will generate the same language as the original one. So as you can see here, what we are doing, we are finding the productions in which there is a left recursive part. So it is A alpha and A delta. We have two rules with a left recursion, A alpha and A delta. We have two rules, beta and gamma, which does not have a left recursion, So now what will happen here, that when you want to derive a string, E starts with TER, So now T is not a left recursive rule. So we can have a chance to use the another rules. And now for T, whatever rules are there, we can apply. When ER will come, again we have a terminal symbol at first, plus or minus or null. So by looking at the input symbol, the computer can take a decision during a leftmost derivation, whether it should select plus TER or minus TER, or it should go for null. So it will add the determinism into the top-down parsing process. So now let us take one more example, because one example is not sufficient definitely. So let us go for the second example. So again, we have the rules here given at the top. A gives A alpha or A delta, where A is the left recursive rules and A is the non-terminal. So we'll rewrite as beta AR, non-left recursive rule, gamma AR, it is again a non-left recursive rule, and for this AR, we'll write as remaining portion from the recursive rule, alpha AR, delta AR, it is also a remaining portion from the non-recursive rule, and we have last sigma. So now if I match with this, can I say that here we have a equal to S? If we write, it is something like this, A equal to S, because we have a left recursion. Then if I match, I can say alpha is equal to 0S 1S. Here beta is equal to 0 1. If I match with the rules, there is no A delta here, so delta is not present. Also gamma is also not present in this grammar. So now as per the rules, we'll write A gives beta AR, so we are writing as S gives beta, so beta is 0 1, AR, so that is SR. And you can take any non-terminal as a new symbol. Now for this SR, we'll write as AR gives alpha AR. So alpha is 0S 1S. So we'll write that 0S 1S. We'll introduce SR at the end. So it is right recursive production now. And we have a null. We have a null symbol. So this is how we'll get the grammar without a left recursion issue. So any query in this second example? Is this clear? Okay, there is one query. This is also done without left recursion if we add E. Okay, I think you are talking about the previous example. Where you want to add E, again it will add the left recursion, nothing else if you add E. Okay, let us see. But I think here you are talking about, right? Again, it will add a left recursion. If you write something like this, I think this is what you want to do. Okay, E gives E plus T or E minus T, or I think E. This is what you are telling, right? This is what you want to do. No, not in. Yes, A gives null. What we have? No, not in left recursion. Yes, can you elaborate, Priyank? So if we add E, I think that is for the previous one. Where you want to add E? Okay, the purpose of we are eliminating the left recursion so that we don't have an infinite loop. We have a clear cut rules so that we have a determinism. We can have only one rule and we'll never go into infinite loop. You can see here that. Okay, let me show you that what problem you are facing. First, when you take this E, right? Now when I write TER, so it is clear because it is the leftmost non-terminal. Now for T, right, whatever rules we have, we'll apply that rules again here, right? Now when ER will come, I can take plus TER. So what will happen? That we are getting a new symbols, plus. So this plus will match with this kind of production. Suppose it is like A plus A. From E, suppose T, we are getting F. Let us assume that. From T, we are getting F. And from F, we are getting A for simplicity. So from T, we'll get F, ER. From F, we'll get A plus T, ER. So now A will match with this A. Now E. So E will check that we have plus. Right? This ER will check. This ER will check. We have plus. Yes. So we'll replace with plus TER. So what is the advantage? That we are not going into infinite loop. On the other hand, if you use directly the previous rules, then what will happen? We want to derive A plus A. We don't know the whole string. We know only one input symbol. So E will start with E plus T. Now again E is there. So we have three rules. So it will try the first rule always. E plus T plus T. Then how it will know that when to replace with A? Right? We got one more plus. Again E is replaced with E plus T plus T plus T. So we don't know when to stop. Well, this will not happen with a grammar in which we have removed the left recursion. As you can see clearly, I am replacing E with TER. So there is no another option with me. So I have to do that. Now T is replaced with F. So F, ER. Again, I don't have any option. So we have to use it. F is replaced with A, ER. So again, I don't have any another option for F. So now it is a straightforward. A I have already achieved. Now ER is there. So I will check for next input symbol, plus. So definitely I will go for the option. I can code the program which will select this when input is plus. Yes. Now where is the query? Yes. Now where is the query? If still you have query, you can unmute yourself and ask.
Hello, sir.
Yes.
I am talking about when we end the string, like in the second grammar of left recursion, like AR to epsilon.
Yes, to terminate the recursion. Right.
Yeah. If that kind of grammar we added in the without left recursion grammar, then also we can end. Then why we are doing this left recursion?
No, but when you know that when to replace with null, how do you know
that problem also faced in this left recursion also, sir?
No, here will not face that. When we'll replace with null, okay, let me tell you that what things will happen. That now here you can see I have replaced ER with plus TER. Clear? I have replaced ER with plus TER. So now I already got the plus, right? Now we have T here. So again for T, I will replace with F. So I will get A plus F ER. Clear? Now for F, I will replace with A. So we'll get A plus A ER. So now whatever string is required, I have already achieved that string and it is a now end of input. So when it is an end of input, at that time I will replace ER with null because now I know that I don't require anything.
Okay.
So null has a specific purpose when the required input pattern is not present, right? That means at that time we have to put null. If all the alternatives will not work, and it will not match with the current input symbol, at that time we'll put null. So it will again get a clear path that we don't require this non-terminal at this point.
Okay, sir.
And that will not happen with the previous case. If I consider here with null, then still I have the option E gives E plus T, E minus T, T or null. You can see. If I replace E with E plus T, let us say. Now for E, I will put null. Null plus T. Because I don't know. I am still not getting A. So if I put null, it will stop everything. Right? So what is the rule? When we can use null? Only when the current input symbol doesn't match with the, is not possible to generate from the non-terminal. Is it clear? Yes, is it clear now? Right, we'll try the null alternative only when the current input symbol of the derivation we cannot generate from the given non-terminal. I will replace ER with null only when I don't have plus and minus, because it will be clear that I don't require that ER now. Let us say, let us suppose we want to generate A only. So what we'll do, we'll start with E, then we have TER as there is no alternative. Now for T, I have F, ER. Now F, I will replace with A, ER. So I have already generated A. So now I know that there is no need to generate plus, minus anything from this ER. So I can replace with null. Is it clear? So we'll use this null only when we cannot generate a string which is the current input symbol from the given non-terminal. At that time, we'll try the null alternative. Okay, so let us proceed. It is better if you have queries, you ask so that it will clear your doubts. Okay, we have one more interesting example, third one. We have immediate left recursion. So let us see that S, then here within parenthesis L, A. So here in this, I don't find a left recursion because S is the leftmost non-terminal, left side non-terminal. The first symbol in the right hand side is opening parenthesis, which is a terminal. The second alternative is A, which is also a terminal. So this rule will be as it is. There is no left recursion in the first rule. Now, when we talk about the second rule, we have L, then L. So you can see the leftmost, the symbol in the first rule is same as the non-terminal, L and L. So we have a left recursion here. So if I match, I will match A with L, alpha with comma and S, and beta with S. This is how I can match with the rules. There is no gamma here. Also, there is no delta here. So now, if I write L gives beta, so beta is your S. So we are writing beta, new symbol, new non-terminal, so it is LR. So L gives beta LR, beta is S here, and for this LR, we'll write the alpha, the remaining portion from the recursive rule. So it is comma S. So comma S, LR, because we want to generate this pattern, comma S repeatedly, and then we have null. Because as you can see, we are generating this pattern only. From L, we'll get L comma S. Again from L, we'll get L comma S comma S. Again from L, we'll get L comma S and comma S. So you can see that we are repeating this pattern, comma S, several times. So that is why it is comma S here, LR, and null to terminate the recursion. So I hope this is clear. There is no query in this. How to eliminate the left recursion? Let us have one more interesting example. So now S2A, this is our example 4, S2A. So there is no left recursion. So it will be as it is. We are not changing it. Now for A, we have a AD. So there is a left recursion. AE, there is also a left recursion. Small a, capital B, there is no left recursion. Small a, small c, there is no left recursion here. Also in the last rule, B gives small b, capital B, C, there is no left recursion. So here the left recursion is only in the second rule, right? So now if you match A is equal to A here, we have alpha that is equal to D, we have delta which is equal to E, we have a beta that is equal to small a, capital B, we have gamma which is equal to small a, small c. We have all the parameters here. A, alpha, delta, beta and gamma. So now as per the rule we'll write beta AR. So beta is your small a, capital B. We are getting this beta AR. Then gamma AR. So gamma is AC. So AC AR. Now for this AR, we'll write the remaining portion alpha AR. So alpha is your D. So DAR. Then delta AR. So it is EAR and null to terminate the process. And the third rule will be as it is. So it is not necessary that in all the rules we have a left recursion. If there is a left recursion in any one non-terminal, we have to also eliminate it. For remaining one, it will be as it is. Okay, so now with this, let us have one more. We have left recursion in more than one rule, A, ABD or AA. Also we have left recursion in the second rule, B gives BE or B. So now here A matches with A, alpha matches with capital B, small d, delta matches with small a, beta matches with A, that is a small a. So now we'll write A gives small a, capital AR, A gives small a, capital AR, because it is beta AR. So we have beta AR. Now for AR, we'll write alpha AR. So alpha is your capital B, small d, alpha AR. Then we have a delta AR. So delta is your A. So A, small a and AR and null. Now similarly for the second rule, A matches with capital A. Sorry, A matches with capital B in the second rule. Then alpha matches with E and beta matches with small b. We'll write capital B gives small b, BR. Then BR gives small e. So that small e will be your alpha remaining portion, alpha AR, and here null. Or no new non-terminal is BR in this particular case. Okay, so far we have talked about a direct left recursion. You can clearly see a direct left recursion in this examples. Yes, is it clear now? We have taken this example. Is it clear now? Yes, Sweta? Okay, so this is what we have done about a direct left recursion. Now we will go for indirect left recursion. Now you can see. So now in indirect left recursion, you can see A gives BA, then AA and C. So here we have two things. If you observe this, right? A to A, there is a direct left recursion. Now, if I replace this B in the first rule, right? If I replace B into the first rule, then again I will get A. You can see that B will give me capital AB. B will give me capital AB, right? You can see here. If I replace non-terminal B in the first rule, I will get capital AB, right? So you can see there is an indirect left recursion here. So what is the first step? So first, let us eliminate the left recursion from A to BA, AA or C. That is the first thing we'll do, right? Because we have to first focus on the direct left recursion. So as a result, when you do this, definitely we can say your beta will be BA, your gamma will be C, right? And your alpha will be A. I hope it is clear if you match with the rules. Alpha is your small a, beta rule which does not have a left recursion, gamma is a rule which does not have a left recursion. So beta will be capital B small a and gamma will be C. So now if we apply that, right, A gives beta AR, so it is capital BA and AR, a new non-terminal, and gamma AR, so gamma is your C. Now for AR we'll write the remaining portion. So we'll write as alpha AR, so it is A and AR and null. Now this B, it will be as it is. Right now in the first step. It will be as it is in the first step. Now we'll use this and we'll proceed further. So now substituting the production of A, right? We can do two things. Either you can substitute B into A or you can substitute productions of A into B, right? So substituting the productions of A in B gives AB. Because if I substitute this, then also it will give me, right, a immediate left recursion for B. It will give me immediate left recursion for B. Because my ultimate goal is we don't want immediate left recursion, right? Because it is creating an infinite loop. So if I substitute A with this, right, then again I will get immediate left recursion in B. You can see in the derivation process, it will be something like this. From A, we'll get B, A, AR. Now I will replace B with AB. So I will get A, B, A, R. Now again I am getting A. So you can see that again from that we are getting the same non-terminal. So this process will be again repeated infinite times. Again I will replace A with BA, AR because it is a non-terminal, leftmost derivation. So I am getting this BA, AR, B, A, AR. I'm replacing A with this BA, AR, and again BA, AR. So again, B is replaced with AB, you can see. So again, we have the same thing. We will go into infinite loop again after 2 steps. ABA, ABA, same pattern will come. So we have to break this thing and we have to eliminate the left recursion. So what we have to do? Substituting the productions of A in B gives AB. We get the new grammar like this. Now you can see that first it will be as it is, BB. Now I am replacing capital A with 2 alternatives. I am replacing this capital A with 2 alternatives. So we have a BA, ARB. We have CB, AR. So because I am replacing with C, AR, so first C, AR, and then B will be at last. We cannot change the order because it will change the grammar. So it is C, AR, and B at last, and D as it is. So now you can see from A we are getting B, C, AR, A and null, and from B we have an immediate left recursion with 2 alternatives C and D, which are not having a left recursion issue. But the first 2 alternatives BB or BA are having a immediate left recursion issue. So we have to do that elimination. So we are getting this. We are focusing on this particular grammar rule. So here A equal to B, alpha equal to B, delta equal to A, AR and B, beta is equal to C, AR, B, gamma equal to D. These are the parameters with us. A, alpha, delta, beta and gamma. So now the first lines will be as it is, first 2, no change in that. Now we'll write beta BR. So beta is your C, AR, B. So we are writing that. Beta BR. Then we have a gamma BR. So here it is gamma, which is equal to D. And now for BR, we'll write alpha BR. So alpha is your B. So alpha BR. Then we have a delta BR. So delta is your small a, AR, B. So delta BR and null. So now you can see, now we will not face that issue. Now we will not face that issue at all. So let me share the screen again. Yes, so this is what we have done. So now if you derive that string, we will not face the previous issue. We'll start with A, then if I take the first one, it is B, A, AR. Now for B, you can clearly see a terminal, C and D. The most important thing is here. You can clearly see the terminal symbol, C and D. So this C and D will tell us whatever string you want to derive. According to that, your computer program will take the alternative. Whether it should take the production C, AR, B, BR, or it should go for another production D, BR. Is this point clear? Right? So that is what the power of elimination of left recursion. That we'll try to pop the terminal symbols as a first symbol. Right? That is the overall goal, you can understand. That our ultimate goal is what? That we want to pop the, it will come out, come like a bubble, right, on the top. So when the terminal symbols will appear as a top symbol or as a first symbol in the right hand side of a production, immediately it will tell you that whether that rule is appropriate in the derivation or it is not. Because if it is a non-terminal, it is not good. Because if we are getting a non-terminal, we don't know whether that non-terminal will be effective or not. It will give me the correct derivation or not. But when you look at the terminal symbols, you can clearly match that with the input string and you can proceed further. So our ultimate goal is that whenever it is possible, try to get the terminal symbols on the top without changing the grammar meaning. So here you can see that in the first production A also, you can see two alternatives. One is capital B, another is small c. So it will clearly tell me if my requirement is small c as a first input symbol, I will go for the second alternative. If my requirement is small c in the derivation process as a first symbol, I will go for second alternative because it is clearly giving me c and we can proceed. If I don't want small c as a first symbol, then I will go for the another alternative B. Right? Suppose we want to derive a pattern like we can say dB. Suppose let us see that we want to derive a pattern dB. Right? My goal is to derive dB. So what I will do, I will start with A. Now I will check. Do I require C as a first symbol? Because my current input symbol is D. Is it clear? My current input symbol is D. So I will check. Do I require C? No. That means that is not the right alternative for me. So I will go for capital B, A, capital AR. Now for capital B, again I will check what is my requirement. Is my requirement C or D? So my requirement is D in the input. So definitely I will replace with D, BR, A and AR. So now once I encounter D in the input, definitely I will go for the next element. That next will be B. So now as you can see, my next requirement is B. So I will check that DB. So definitely for BR I will select BBR. Right? I will select BBR. So now what will happen? That I will write as D, B, BR, A, AR. Now I have already achieved this DB. So now what is my next requirement? It is the end of the input. So as it is the end of the input, I will generate this DB. I will replace BR with null. So I will get A, AR. Now here it is A and here my requirement is end of the input. So you can see there is a mismatch, right? You can see clearly the mismatch here because I have derived DBA and AR. My requirement is DB and empty string. So that means what? This string cannot be derived from this grammar rule. I cannot derive DB from this grammar. If my requirement is DBA, then I can proceed further. Is this point clear? So our terminal symbols will help us to decide the correct move. Our terminal symbols will help us to always decide the correct move. So our goal is we want to take the terminal symbols as a first symbol in the grammar rules so that we can complete the process very fast. Is this clear? Can we proceed? Yes, can we proceed? Yes or no? Suppose if I want to derive this DBA, if the next symbol is DBA, then I can proceed here and I am able to derive that string properly. If I want to derive this DBA, then I can proceed further. I got DBA, so now I will replace AR with null. That also I can do. So I have D, B, A only. I will replace with null. Yes, is it clear? That what is the advantage of left vectoring or left recursion? Ultimate goal is we want to get a terminal symbol as the first symbol. As and when we'll get a terminal symbol, we can proceed in the input string and we can derive that input string fast. It will not create a non-determinism and our parsing process has lesser number of steps. We don't have to do any backtracking. As much as possible, we can avoid the backtracking by this. Yes, is this clear? Okay, so now let us proceed further. One more example here we have. So now this is a complex example. So now we can see that in the first step, A gives BC or A gives BC or A. So there is no left recursion. It will be as it is. Now when we come to the second rule, right? When we come to the second rule, then you can see B gives CA or AB. So now as we have gone through the first rule, I can replace A in the second rule. Same thing we have done in the previous example. If there is immediate left recursion, we have to eliminate and then we have to go for the next step. So here there is no immediate left recursion in rule 1. In rule 1, right? Detailed algorithm you will also learn in the next semester for this. But here we are not going into that detail. Here it is also. These are the algorithms for that. But you will learn more about that in the 7th semester. Right now we don't have that in the syllabus in your textbook, so we are not doing that. Now what we'll do in B gives CA or AB. So there is no left recursion directly. There is no left recursion directly, but I can replace non-terminal A here because A is already visited. I can replace the non-terminal A here as A is already visited. So that is what I am doing. You can see B gives CA. I am replacing A with BCB and BC AB because second alternative for A is A. So AB, the second alternative. Is it clear? So it is very simple. In the first step, we cannot do anything as there is no previous rule. As there is no previous rule, we cannot do anything. Now in the second step, can we have an immediate left recursion? You have to ask that question. So there is no immediate left recursion, direct left recursion. Can we do a replacement? Yes. So we have already gone through rule 1. So we can do the replacement of rule 1 now. So that is what I have done. Now again we have to ask, by doing a replacement, are we getting a left recursion? Immediate? Are we getting the immediate left recursion? Yes. So that is what we are doing here. We are removing that. We are removing the immediate left recursion. So these are the 3 questions we have to ask repeatedly. Do we have an immediate left recursion? Yes or no? If yes, apply it. If no, can we do any replacement? Yes or no? If yes, we can do the replacement. After replacement, are we getting a left recursion immediate? Are we getting the immediate left recursion again? Yes, do that. These are the 3 rules you have to keep in your mind. Rule 1, first immediate left recursion you have to eliminate. Rule 2, if it is not there, do the replacement if possible by the previous rules only. By the previous rules only, not by all the rules. And then after doing a replacement, if we get immediate left recursion, we have to do that. So here we have done. Now when we reach to rule number 3, right? We have two previous rules. So that is what we are doing, AB or CC or A. So I will replace A. With this. I am doing a replacement with non-terminal A. And we are getting this. Right? We are getting this. Now, what we'll do? Further, you can see. We'll check. Can we have a replacement for B? Right? Can we have a replacement for B? Yes. So we have a replacement for B also. So that is what we are doing here. We are doing a replacement for this B here. And this 3 will be as it is. The first two are the replacement for B. Once we have done all the replacements, now we'll remove the immediate left recursion. Right? We'll remove the immediate left recursion from this C. The same thing we have done here, you can see. The first rule, there is no left recursion, immediate or anything, so it is not applicable. In this second one, can we do the replacement? We are doing the replacement. And then we'll remove the immediate left recursion which arises from that. Now in the third rule, we have two previous rules. We are doing the replacement of first rule. We'll do the replacement of the second rule. Once all the replacements were done, we'll remove the left recursion. So this is a very complex example. Yes, if you have any query in this. Yes, are you getting this? So that is the purpose of the for loops. That in the first rule, we don't have any previous rules. So, and also there is no immediate left recursion. So we cannot do anything. In the second rule, we have replacement possible. So we are doing the replacement. And then after replacement, we are getting the immediate left recursion. As we are getting the immediate left recursion, we are removing the immediate left recursion. Now, when we reach to rule number 3, can we have a replacement possible using rule 1 and 2? So the answer is yes. We can do the replacement using rule 1 as well as rule 2. So first we are doing a replacement by rule 1. We'll get a new grammar. Then we'll do the replacement by rule number 2. We'll get the new grammar. And then last, after both the replacements, we'll remove the immediate left recursion. This is a very complex and interesting example. Same thing we have done in the previous case, if you can recall. Let us see that. The first, right? Because it is a first rule. So no previous rule is there. As it is a first rule, there is no previous rule. So we are doing the immediate left recursion because it is the first rule. Keep in your mind, don't mix these two. Here we are applying immediate left recursion first because there is no previous rule. And then after that, for the second rule, we'll do the replacement first by the substitution. We'll replace the non-terminal by the first rule. And once it is done, then we'll remove the immediate left recursion. Right? So when the first rule is there, there is no previous rule. So if there is immediate left recursion, we have to apply. It is applicable to the first step. If there is immediate left recursion, we have to apply because there is no another replacement possible. For the second rule, replacement is possible by the first rule. So first we'll give a priority to replacement. And then at last we'll directly apply the left recursions. Okay, so now we have these two practice problems. So can anyone solve the second one? Let us go to the practice problem 2 in this remaining 2 minutes. Can anyone solve this second problem? The first rule, S gives A or B. So there is no left recursion, as you can see. S gives A or B. So we cannot do anything. There is no immediate left recursion. There is no immediate left recursion. So we cannot do anything. And no replacement is also possible. Now for the second rule. AC. Now here replacement is possible for S. So we'll write that AA, B, or DD, and E. Is this clear? Yes, is this clear? Okay, now for the second rule, we can apply the immediate left recursion and we can remove it. So we have BD, AR, or we have E, AR. And for AR, we'll write as remaining portion C, AR, or AD, AR, or null. It is alpha AR, then delta AR, and then null. Is this clear? So this will be the final grammar. And S will be as it is. No change in the S. A or B. So this will be the final grammar. If I want a terminal symbol B, I will go for the second alternative. Otherwise, I will go to capital A. Now, capital A, you can see two terminal symbols are there, B and E, as a first symbol. We have two terminal symbols here, B and E, as a first symbol. So that is what we'll apply as per the requirement. And then for AR also, we have terminal symbols as a first symbol. C is there, small a is also there. So we can select the choice properly. And if not, none of these choices work, we'll replace with null. We'll replace with null. I hope it is clear now. Okay, so now we need at least 45 minutes to complete the syllables. Around 40 to 45 minutes to complete the syllables. So Monday our lecture will be there. Clear? We have last lecture of TOEFL to complete the remaining syllables. We'll meet Monday as per the timetable, 1:30. Our Monday slot is at 1:30, 1:30 to 2:30. So we'll meet from 1:30 to 2:15, around 45 minutes maximum to complete the syllabus. Thank you.